In this video, we establish the non-planarity of two, as will turn out, two very important graphs in terms of non-planarity. And these two graphs are K5 and K33. So actually, we quickly proved this earlier, but I'll run through the idea again that the graph K5 is non-planar. So K5 has, so M is 5 choose 2. So 10 edges in K5, n of course is 5. And if we compute 3n minus 6, 3n minus 6 then would be 9. And so here we have m plus 10 is greater than 3n minus 6. And so very quickly, based on our previous work, so that is by using theorem 10.4, by theorem 10.4, K5 is non-planar. Right, so there's no way to draw K5 in the plane without edges crossing. Of course, since K5 is a subgraph of any larger complete graph, so as a consequence of this, Kn is non-planar for each n greater than or equal to 5. So this gives us an infinite class of graphs that are non-planar, in particular all of these complete graphs for n at least 5. So K33 is another graph we'd like to look at, and actually K33, there's a famous problem that goes along with K33, and this is the houses and utilities problem. So the idea is, say we have three houses. I'm just going to draw a rectangle. House 1, house 2, and house 3, and we have 3 utilities. Utility 1, maybe this is gas, electric, and water. And so we have house 1, house 2, and this is sort of a classic puzzle. Is there a way to hook up each house to each utility? And you don't have to draw straight lines, you can draw curved lines, but hook up each house to each utility with no two edges crossing. Right, so maybe I could do house 1 to gas, electric, and water, and maybe house 2, maybe I'll go around like this. House 2, I'll do something like this to get them all. Maybe I can go like that for water. And then house 3, I can hook up to water. I can hook up to electric, but then I can't get to the gas. So this, of course, doesn't prove it, but it suggests that we're going to need to try something really out there in order to hook up gas to house 3 and get all 3 of these houses hooked up. As it turned out, there's no solution to this. There's no way to do it. And so what we're really asking for here in graph theoretic terms, we're asking if K33 is planar or not. That's really the question here. And as it turns out, it's not. So why is K33 not planar? Sorry, let me jump back over here for a second. So let's think about K33. K33, let's try and use theorem 10.4 on this. So we'll see if it breaks the bound on the number of edges. K33 has, let's see, m equal to 9 edges and n equal to 6 vertices. And 3n minus 6 here would be what? 18 minus 6, that's 12 edges. So m is less than or equal to 3n minus 6 here. And so theorem 10.4 does not tell us that this is non-planar. Of course, it doesn't tell us that this is that it is planar. Just tells us it's not a proof that it's non-planar. So we have to do something else here. And as it turns out, we'll have to use the property of K33, the fact that it's bipartite, and hence doesn't have any triangles in it. So let's prove this. So proof. So K33, actually I don't want to start with that. Let's let So suppose it is. Suppose it is planar. Then n, our number of vertices, is 6. M is equal to 9. And so if it were planar by Euler's identity, we would have n minus m plus r equal to 2. So that would be what? 6 minus 9, negative 3 plus r equals 2. So that would tell us r was equal to 5. So if it's planar, then we have 5 regions, and let's call them R1, R2, R3. So we'll say let there be a planar embedding of K33. Then we would have 5 regions for K33, and let m sub I be the number of edges on the boundary of R sub I. So since K33 is bipartite, well, then there's no triangles, right? There are no triangles. In particular, generally there's no odd circles, but in particular there's no triangles. And so what that means is that Ri is at least 4 for each I. All right, so also K33 is bridgeless. And what that means is every bridge, in the world of planar graphs, non-planar graphs, bridge means it's only on the boundary of one region. If it's bridgeless, that means every edge is on the boundary of exactly 2 regions. And so that means I can count the number of edges. By counting the number of edges around each boundary, I'll get twice the number of edges. So on one hand, the sum of the m sub i's, counting the edges on the boundary of every cycle, or on the boundary of every region, that'll give me twice the number of edges, which is 18. Oh, sorry, I used E here from the polyhedra stuff, 2m, which is 18. On the other hand, every m sub I, I said r sub I is greater than or equal to 4. That doesn't make any sense. I mean, m sub I is greater than or equal to 4, right? The number of edges around each region is at least 4. On the other hand, the sum of the m sub i's, well, each one has at least 4, and so this is greater than or equal to sum of 4 from I equals 1 to 5, and so that's 20. So what do I have here? I have that 18 is greater than or equal to 20. And that's a contradiction. So that is, if K3 theory was planar, all of this stuff would follow, and we'd end up with 18 greater than or equal to 20. And so that's false. So K33 is non-planar. There's no way to draw K33 in the plane without any 2 edges crossing. So as I mentioned before, it'll turn out that K5 and K33 are actually 2 very special non-planar graphs. And what we'll see is that in some sense, every non-planar graph contains either K33 or K5, not directly as a subgraph, but in some form. So we'll have to develop this idea a little bit more in the next few videos. I'll see you there.